we're going to discuss a whole new number called e. And I did say that right. E is a new number. And, well, it's not new, but it might be new to you. And it's approximately the number 2.72, if you round up. And E is a number that can be found on your calculator if you have a scientific calculator. And so it's kind of like pi. It's an irrational number that can be approximated. And we use it especially when we're talking about exponential growth and decay. When we are simplifying expressions with the letter E, we can treat it like a variable. And so you're basically just using exponent rules, but the difference is E is not a variable, so the values can be estimated by using your calculator. But just a quick reminder of exponent rules. Whenever we're multiplying, the exponent rules say that we add those exponents together, so we get E to the 9th. And I would leave my answer like that. But again, because E is actually a number, we can calculate that or approximate it by using your calculator. The next one, division. Division property says that we divide the numbers. 24 divided by 8 is 3, and we subtract the exponents. 8 minus 5 is 3, so that would be 3e to the third power. The power to a power rule says that we're going to distribute this exponent of 2 to all the exponents on the inside of the parentheses. So it's going to become a 3 squared. And 2 times negative 4x is negative 8x. So if I simplify that even further, we get 9 over e to the 8x power. Move negative exponents to the denominator. For the next one, when we're taking the cube root of 27 is 3, and the cube root of e to the 6x is e to the 2x. If you aren't sure how I got that, imagine if you had e to the 2x times e to the 2x times e to the 2x. If I were going to calculate this, they all have a common base of e, and the multiplication rule says that I add these exponents, 2x plus 2x plus 2x is 6x. So that means when we take the cube root of e to the 6x, we get e to the 2x. Oh, there's that same example again. We'll ignore that. Okay, so let's try a couple more. On this one, we're going to distribute that 3. So 10 to the third power, e to the negative 9x. And I can simplify that even further as 1,000 over e to the positive 9x power. Down here, another multiplication problem. The rule says we multiply the coefficients and we add the exponents. And then for the last example, this is the trickiest of them. We divide the coefficients, 8 divided by 6. I'm just going to leave that as 4/3. And when I divide with a common base, we subtract the exponents. Well, the exponent on this e in the numerator is 1. And 1 and 2x are not like terms, so I can't really subtract them. So I would leave that as e to the 1 minus 2x power. When we are graphing exponential functions where the base is e, because the base e is always bigger than 1 to approximately 2.72, it would seem it would always be an exponential growth function. But what can change it to a decay function is if there is a negative exponent. If the exponent is negative, then that creates a reflection over the y-axis. And so that exponential growth function, when you reflect it, becomes an exponential decay function. So just keep in mind that negative exponents can change a growth function to a decay function or vice versa. Just like any exponential growth or decay function, there is an asymptote, a horizontal asymptote, and for these parent functions, that asymptote is going to be at y equals 0, or the x-axis. And the only thing that would change where that asymptote is by moving the graph up or down. That transformation would move the asymptote up or down as well. So when we're graphing these functions, these are just normal exponential growth or decay functions. We're going to make it XY charts. There's going to be an asymptote, a horizontal asymptote. This function is not being moved up or down, so the asymptote is at y equals 0 or the x-axis. And then just like normal, you're going to plug in your values. -2, -1, 0, 1, and 2 are my favorites to plug in. And you can just plug this straight into your calculator. If you have a scientific calculator, you should have an E button that you can raise to any power. Just make sure you're typing things incorrectly. You might want to use order of operations, do the exponent before you multiply. But I'm going to give you, why don't you pause it, give yourself a chance to calculate those values to make sure you're typing it incorrectly, and then I will give you each one of those values. So these are the values you should be getting. When we graph the function, we can see that it's exponential growth. The domain, because it's an exponential function, is all real numbers. Your range is limited because of the asymptote. In this case, all of those values are above the x-axis, so y is greater than 0. Let's try another one. So another example. This one is also going to be exponential growth because our base is bigger than 1 and there are no reflections going on. Because we are not moving the graph up or down, there's no plus or minus. That would be the transformation that moves the graph up or down. Our asymptote is going to remain at the x-axis, or y equals 0. And this time I'm going to change up what numbers I plug in, because in my exponent I have 1/2 times x. Just to get nice pretty numbers in there, instead of plugging in -2, -1, 0, 1, and 2 like I normally would, I'm going to plug in all multiples of 2 to make those exponents nice and pretty. So -4, -2, 0, 2, and 4. And so again, the reason why I did that is now when I take 1/2 or 0.5 times -4 power, that becomes the -2nd power. Just a little bit more simplified to type into your calculator, but again, it does not matter. You do not have to do that. You can plug in any numbers that you want because our domain is all real numbers. So let's see, this one would be 2e to the 0 power, this would be 2e to the 1st power, and this would be 2e squared. So try finding those values. So you can see another exponential growth function where that asymptote is 0. These numbers would just keep getting closer and closer to 0. Our domain is all real numbers because it's always all real numbers for exponential functions. And our range is y is greater than 0 because they're all above that asymptote. For this function, our base is bigger than 1, e is bigger than 1, but we have a negative in the exponent, which is a reflection over the y-axis. So what would normally be a growth function is actually going to become a decay function. I'm going to plug in all my normal numbers. And when I do that, when I plug in -2, my exponent becomes -2 or +2. Plugging in -1 gives me an exponent of +1. Plugging in 0 gives me an exponent of 0. Plugging in 1 gives me an exponent of -1. And plugging in 2 gives me an exponent of -2. So again, we're going to find each of those values. And I forgot to mention on this one, because we are moving up 1 this time, my asymptote that is normally on the x-axis, or at y equals 0, is going to be at y equals 1. Everything got shifted up 1. So then when I go to graph these, remember it's going to be exponential decay. It's going to go down from left to right. And it's going to get, the numbers are going to get closer and closer to 1. So 1.5, 1.2, 1.1. And they're just going to keep getting closer and closer to 1 because that's where our asymptote is. The domain is all real numbers. The range, all of those values are bigger than 1. Let's try one more graph. So another example where the base is bigger than 1 because e is always bigger than 1. But because there's a negative alongside in our exponent, that's going to be a reflection over the y-axis, which changes that exponential growth function to an exponential decay function. Other things that's happening with this graph, it's being moved up 1. So my asymptote, instead of being at 0, is going to be up here at y equals 1. And it's being moved right 2. Because it's being moved right 2, I'm going to plug in, instead of plugging in -2, -1, 0, 1, and 2 like I normally like to, I'm going to move all of those to the right 2. And the reason I do that is because now when I plug in 2, 2 minus 2 is 0. And I like for the middle number that I plug in, I like for that exponent to be 0. It's a personal preference thing. I just enjoy that. So that means when I plug in a positive 1, my exponent is going to be -0.75 times -1, or positive 0.75 as that exponent. When I plug in a 0, I'm going to have -0.75 times -2, and so on and so forth. So let's pause again and try to find those values. So make sure that you can check or plug those, each one of those into your calculator correctly without error, that you're getting the same values that I'm getting here. And then always just double check that the graph looks the way that you thought it would. We wanted it to be exponential decay, and it is moving down from left to right. We wanted the asymptote to be at y equals 1, and when we look at our values, they're definitely getting closer and closer to 1. So our domain is all real numbers, and our range is y is greater than 1. The last thing we're going to end on is calculating how much money you earn with interest when the interest is compounded continuously. So when the interest is compounded continuously, we use this formula where the P is the principal, or how much you're putting in. E, remember E, even though it looks like a variable, is really a number. That's the 2.72. R stands for rate, and we always write that as a decimal, and T stands for time in years. So when I'm reading this, you deposit $4,250. That's your P. That's what you're starting out with. That's what you're investing in an account that earns 5% annual interest. So 5% is your rate, but we write the rate as a decimal. 5% as a decimal is 0.05. It tells us that the interest is compounding continuously. That just means that we're going to be using this formula right here. And how much do we have after 20 years? That's the time. So A equals, the principal is 4,250. E to the RT power. When you're typing this in your calculator, just be careful. We want this whole thing to be raised, or to be the exponent. So if it's helpful to calculate 0.05 times 21st, you can do that first. But go ahead and find that solution. 0.05 times 20 is 1. So we have 4,250 times e to the first power. And if you put that in your calculator, you get about $11,552.70. Would be how much you have after 20 years.